All right, the Unit 2, we learn about electrostatics, which is charges moving around from one object to another and sort of collecting on objects so things can have a net charge. Typically, most particles are going to have be neutral at first because they're made up of atoms that are a combination of protons, neutrons, and electrons. And the protons are going to have a positive charge, and the neutrons have no charge, and the electrons are going to have a negative charge. Now in chemistry, we kind of learn this arbitrary value for charge that protons are just plus, or electrons are just -1, but there actually is a charge in coulombs that is 1.6 times 10 to the negative 19th, which is called the elementary charge. And, oops, that one's positive. And then this one's negative 1.6 times 10 to the negative 19th coulombs. Right? Now the location of the protons and the neutrons is in the nucleus of the atom, whereas the electrons are around in shells outside of the atom, and therefore the electrons are really the ones that are going to be doing the transferring. Right. One more thing I want to note here before we move on and talk about charges moving from one place to another. Let's look at the mass of these things. This is going to come into play a little bit later when we start talking about these charges moving around. So a neutron and a proton have a mass of about 1.67 times 10 to the negative 27th kilograms. But for a electron, it's about 9.11 times 10 to the negative 31 kilograms. All right, so like I said, electrons will move from one place to another, and as a result of the transfer of electrons, things actually gain charge, right? So objects can gain a net charge. All right. So if I were to take like a piece of wool and I were to rub it on a rubber rod, the wool at first, both of the objects are going to be neutral. So let's just say this is a piece of wool and here we've got a rubber rod, right? And at first they're both neutral. But when I bring them in contact with one another and I rub them against each other by using friction, so this is one way charge can be transferred, the wool actually will lose its electrons, some extra electrons to the rubber. So the rubber will pick up a negative charge, and because the wool has lost electrons to the rubber rod, that means the wool would be left with a net positive charge, right? Now, let's say this thing gained a charge of like, say, -2 nanocoulombs. Because of the law of conservation of charge, so charge is always conserved, whatever the charge at the beginning would have to be equal to the charge at the end within the system, right? So if at first the charge was 0, the net charge was 0, if I moved -2 nanocoulombs over here to show that charge is conserved, I would have to say that +2 nanocoulombs must remain here so that the net is still 0. Now, if I wanted to figure out how many electrons actually made the jump from the wool to the rubber, I can actually just use the equation that the net charge that is gained by something, and we usually use a capital Q for that, is if I divide that by the charge of each individual electron, or the elementary charge up here, then it would give me the actual like numbers of particles that made the jump from here to here. Right? So that's charging by friction, but we can also charge by, a process of induction and conduction, right? So let's say let me go to the next page here. So let's say that I had this negatively charged rubber rod, and I brought it close to a conducting sphere, right? And the conducting sphere is going to be full of protons and electrons, right? And so by bringing the negatively charged rod close to it, it actually forces the electrons to be pushed towards one side, right? That means this side would have a relatively positive charge. Now, the protons didn't flow over there. It's just that all the electrons on this thing sort of crowded off to this side. This thing's still neutral, but it has some polarization here where we have a positive side and a negative side. Now, because this is now slightly positive on this side, that means that it's going to be attracted to the negative rod. So charged objects attract neutral objects. All right, now notice that these things didn't come in contact with one another. We just say that this has induced this polarization on here. Now, if I really wanted this thing to have a complete charge, so this conducting sphere to have a complete charge, what I could do is I could take this sphere and actually ground it. So, attach it to something else that's bigger where the electrons would want to flow across. So maybe the Earth, right? Or I could just touch it with my hand. And so those electrons would flow off of the surface of that sphere in order to spread out over here. And I would then be left with a conducting sphere that has a net positive charge. So that's the process of charging objects by induction or conduction. All right, so let's go ahead and then take a look at what if I had two conducting spheres and I were to attach them to one another. So let's say I have two conducting spheres that are exactly the same size, right? And the same size is important. And let's say this one had a charge of -6 nanocoulombs, and this one had a charge of 10 nanocoulombs, something positive, right? So somehow they got this charge, right? So the net charge right now at the beginning would be equal to, I've got -6 here and +10 there, it would be +4 nanocoulombs, right? If I were to connect them by a wire, then the electrons on this negative thing would rush across and go over onto this sphere. And because they're the same size, they would actually move over there until both of the spheres actually reached equilibrium and had the same charge. Because they're it's really that the electrons are going to move until they reach an equipotential. We'll talk in a minute about what potential actually is. But when they have the same size, that also means that they're going to have the same charge. So the net charge, when all is said and done, still has to be a +4. So if they're both the same size, that means that now, in order to have the same net charge of +4 nanocoulombs, that means that one must be +2 nanocoulombs and the other have a charge of +2 nanocoulombs. All right, so up here we kind of talked about bringing an electric rod, so a negatively charged rod, close to a conducting sphere in it, push those electrons off to the side. Well, anytime we have a push or a pull in physics, that is a force, right? So we're going to talk about now a force called an electric force. Now, this force occurred without these things actually touching each other, right? So that's one of our field forces, and we've already seen one of our field forces was our other inverse square law, which is the force due to gravity, right, is equal to a constant g m1 m2 over r squared, right? So if we're going to then look at electric force as being a similar sort of inverse square law force, we have Fe is equal to K, which is a constant, Coulomb's constant. Oop, I almost wrote M. Oh, I wrote G. Sorry, I mean Q1, Q2 over their distance apart squared. Now this K, there's another way of writing this K, which is 1 over 4 pi E sub naught, which just has to do with vacuum permittivity. But if we just kind of keep in mind that these two numbers are interchangeable, we should be pretty good for this class. So this is the quantity of the electric force. All right, so if I had a charge, or a big sphere, let's say it's a positively charged sphere, and over here I were to put a little point charge in it, and let's just say that it's negative, right? So let's say this is a negative, little point charge, little electron or something over here. Right, so there is going to be a force that this sphere exerts on this guy over here, right? So if I wanted to, draw what that force would be, it would be an attractive force, because one of the differences between this force and this force is this can be either attractive or repulsive, right? So we know that like attract and opposite repel, whereas this one is only an attractive force. So here we would actually, if we were going to draw a free body diagram, I'm not actually going to draw it on here, but you would draw a arrow in this direction indicating that there's a force on this thing towards this sphere, right? So I mentioned that these were field forces, right? So field forces means that there's a region of space around the outside of this thing where if a charge were to go into it, a force would act on it. So we define the electric field as being the electric force on some charge that's in that field. So it's a force per unit charge. So the unit that we get is newtons per coulomb. Now, another way to actually look at quantifying the electric field, because the electric field is in existence even if there's not a charge there. And this equation is dependent on there being a charge there. And so there might not be one there. So can we figure out what the strength of the electric field at some point around the outside of this conducting sphere is without actually having a charge in it? And the answer is yes. So if we go ahead and we just look up here and we use our force equation, so this is electric force, and I'm dividing by Q in, right, so it makes one of these Q's cancel, I get the other equation for electric field is where we have K Q, and that's now the Q making, because the Q in has canceled, so this is the Q that's making the field all over R squared. Right? So I'm going to leave it at that for this video, and then in the next video I'm going to introduce the idea of electric fields and electric potential and sort of compare and contrast those and talk about electric potential energy and hopefully get to capacitors as well.